Okay, let's look at another application of the cross product. And this application is kind of the same flavor as the application of the last video, which was to relate the magnitude of the cross product to the area of the parallelogram spanned by the two vectors that you're taking the cross product of. And this application, we're going to look at another product called the box product. Okay, so let's say we have two vectors, u and v, and we know how to calculate the area of the parallelogram spanned by u and v. But now let's extend this to a third dimension, right? This is living inside R3. And so let's see if we can extend our applications to the maximum dimension here, right? So if we have this normal vector, u cross v, this triple spans a parallelepiped. Parallelepiped. I hate that word, but that's what it's called. So we have a parallelepiped here spanned by u, v, and the cross product. And so this isn't a very good picture. Let's draw a different picture that looks less cubic. So we have u, v, u cross v. Let's take a copy of v, copy of u, and then 3 copies of u cross v. And then let's just complete the picture here. And what you can see is we have a 3-dimensional analog of a parallelogram, and we call that a parallelepiped. Let's just call it a box. I like that better. And so now we have this box living inside 3 dimensions. And you could ask yourself, what is the volume of this box? So let's give the box, let's denote this by the variable beta. So we'll call this box beta, and we want to calculate the volume of this box. Well, the volume of this box would be the area of the base times the height, right? So let's look more abstractly here for a second. So let's just say you have a parallelepiped with side lengths A, B, and C. Then what would the volume of this be, right? Well, the volume of this would just be the area of the base parallelogram. So let's call the base here P, and then some height, right? Let's just say H here. So this is the volume of the area of the base times the height. Well, we know how to calculate the area of the base parallelogram here, but what do we do for the height? And to account for the height and to calculate the volume, we use the following formula. So the volume of the box beta is equal to the absolute value of, so let's say here, the side with length A, this is a vector u, and then with B, vector v, and here's some other vector w, right? Then the volume is the absolute value of u dot product with the cross product of v cross w. So let's understand why this gives us the volume. And this quantity here, I'll box it. This is called the box product. Let's see why this gives us the volume. So let's say we have vector u, vector v, and vector w. Okay, let me finish my picture here. That's terrible. Okay, so what's the area of the base parallelogram here? Well, the area of the base parallelogram is going to be the magnitude of u cross v, right? And then we need the height. And so we would need to dot that with u, right? Or with w, excuse me. And you may ask, well, you did this in a different order, right? Like first you took the cross product, oh, sorry. First you took the cross product of u and v, but in the formula, it says the cross product of v and w. Well, it doesn't matter because we have the following proposition. It says u dot v cross w is the same as u cross v dot w, right? And so you can kind of switch the order in which cross product you compute first. So let's do an example here. Let's find the volume of the box constructed from the following three vectors. So let's say we have u is 1, 2, -5, v is 1, 3, -6, and w is 3, 2, 3. Okay. If we want to find the volume of this parallelepiped, what we need to do is we need to compute the absolute value of the box product here. So let's do that. Let's stick to the original definition here. So first, let's compute v cross w. So v cross w is going to be the determinant of the 3 by 3 matrix ijk, 1, 3, -6, and 3, 2, 3. The result is going to be, well, for the first component, right? Here, just for review, we start with I hat, we block out the row and column that I hat belongs to, and then we compute the determinant of the resulting 2 by 2 matrix. So we would have 9 minus, so I'll write it out explicitly, 9 minus -12. And then for the second entry of our cross product, we block out the row and column that j hat belongs to, and then we take negative 1 times 3 minus a -18, right? And then for the last entry, block out the row and column for k hat, and then we have 2 minus 9. Our result is going to be 21, and then 3 plus 18 would be 21, but it's -21, -7. Cool. So here is the cross product of v and w. And now we need u cross, or excuse me, we need u dot v cross w, which means we have 1, 2, sorry, -5 dot with 21, -21, -7, which will be 21 plus 2 times -21 plus -5 times -7, which is going to be 21 minus 42 plus 35, which should be -21 plus 35 is 14. And so the volume of the parallelepiped spanned by these three vectors would be 14. Okay, and I think that's all I want to talk about for the cross product and its geometric applications. If you've taken Calc 3, hopefully a lot of this is review and I'm boring you to sleep. if I'm not boring you to sleep, then I hope this was kind of a good introduction to the cross product and how to understand it. And so now what we'll do next week is, with these kind of notions of vector algebra extended to n-dimensional space, we'll start to tie all of these notions back in to the matrix theory that we've been doing so far. And we'll see what kind of theory and applications we can get from combining these notions here. So that's what we'll do next week.